Okay, so Assalamu alaikum and welcome everyone. I am Mohsina Asif, a science communicator at the Khwarizmi Science Society, and I would like to thank all of you for joining us today. We are going to be hosting a very interesting talk today on quantum theory. The exact topic is quantum theory with pictures, and the speaker is Muhammad Hamza Waseem. So before we start with that talk, and while we are waiting for more people to join us, I would like to say that for those of you who have not yet watched our talk on quantum computing, which we hosted last month, in which we had Dr. Michael Castriano as the guest speaker, then please do watch that video because it's very interesting and it's actually very educational. So you can watch that on our YouTube or our Facebook channel. So today, the topic which Hamza Waseem is going to be talking about is how anyone can understand quantum theory with pictures. And before we dive into that presentation, it's important that we introduce you to who exactly is Muhammad Hamza Waseem. And so he's basically a very talented person. He is currently a DPhil researcher at Oxford University. He is studying condensed matter physics. His research interests include hybrid quantum systems and quantum magnetics, and he's also the Rhodes Trust Scholar from Pakistan. He was selected in 2019 to pursue a degree in DPhil at Oxford University. Before this, he has done his undergraduate in electrical engineering, and during his senior year project, he worked on establishing the first single photon quantum laboratory in Pakistan. And he also has a published book, which has been published by the Institute of Physics. Other than this, Hamza is also a very active science communicator. He has co founded the popular science online magazine called Spectra, and he is also an active member of Khwarizmi Science Society and is one of the key organizers of the Lahore Science Mela. So, without further delay, I would like to welcome Hamza. Hi, Hamza, could you please switch on your video?
Thank you, Mohsina, for your kind introduction.
Hi, how are you? Yeah.
I'm good. I have still not figured out how to share my screen.
Okay, is that option not showing?
No, it's not showing on my screen.
Okay. You're using Google Chrome, right?
I tried Google Chrome, doesn't. It says that I have to use Safari on my iPad.
Oh, okay. So, um, okay, if you could send me your slides, then I could maybe share the screen and we could do something of that sort.
Okay. I am emailing you my slides.
Okay. So we'd like to request the viewers to wait for a few minutes while we sort this out. But we assure you this is going to be very interesting as Hamza is going to explain that how pictures can be used to understand quantum theory. And as somebody has commented, Hussein says that I wish somebody could explain me a few basics of quantum physics in an illustrative manner. Then, well, Hussein, this is exactly what this talk is going to be about. So please do stay tuned for this. Just a few more minutes. Also, I'd like to say that we're going to have a dedicated question and answer session in the end. So, whatever questions arise in your mind during the presentation, please do ask them in that last 10 or 15 minutes that we're going to have.
Okay, so Mohsen, I have sent you my slides.
Okay. Okay, so just a few more seconds. We have the slides ready. All right, so is this fine, Hamza?
Yeah, I can see them. Could you go to full screen?
Okay, wait a second. Wait. It won't be possible to go into full screen because
Okay.
I've opened this in Google Chrome. Yeah.
Okay, this is fine. So go to the next slide, please.
Okay.
Okay. So
Just a second. Yeah. Okay, this is fine.
should I start?
Yeah, you should.
Okay. So first of all, I would like to apologize for the technical issues. Today, I'm going to talk about quantum physics and how it can be understood and taught using pictures only. Next slide, please. So if you have seen the poster that was advertised on social media, you might have thought that I would be showing you some memes or cartoons about quantum physics, just like this one, which has been in circulation on Facebook and Twitter. But unfortunately, I won't be showing you these kinds of pictures, but I'll be showing you lots of diagrams and pictures. So there will be minimal mathematics while we talk about serious quantum physics. Next slide, please. So this formalism or new paradigm for studying or thinking about quantum physics is called quantum picturalism. Quantum picturalism is based on using process theories to describe quantum processes and how they interact. Next slide, please. Most of the content that I will be talking about can be found in this book called Picturing Quantum Processes by Bob Koch and Kissinger. None of the content in these slides will be original. I am just a messenger trying to pitch this new paradigm to you people. Next slide, please. Yeah, so we will describe quantum theory in terms of processes and next slide, please. Processes and how they connect. So a process is simply a box that has a few wires. some wires going in, some wires going out, and these boxes can be connected. And we can also look at how these wires interact. Next slide, please. Now, why do we want to look at quantum theory in this way? It's because this is quite simple and intuitive. Next slide, please. So I'm sure that most of us will agree that the equation on the right side of OR is much simpler as compared to the equation on the left side. Next slide, please. So using quantum picturalism, we can get fresh insights about quantum physics. This also provides us new tools for doing calculations for quantum information and quantum computing. And essentially, this is a theoretical sandbox. You can do all kinds of thought experiments using this formalism. Next slide, please. So what is a process? Let's try to understand processes using some examples. We have all heard about functions. A function is simply a machine that takes in a few and gives out some other numbers. So this function takes in two inputs, x and y, and gives us a number as an output. Next slide, please. In graphical language, we can represent it like this. So the box represents function, and the two wires at the bottom of this box represent the inputs, and the single wire at the top represents the output. Now, throughout this presentation, you have to remember that we are looking at these processes or these pictures from bottom to top. The inputs are at the bottom and output is at the top. Next slide, please. So as I said, the box is the process, and the technical word for these wires is types. So types basically mean the inputs and the outputs. In this case, the types are real numbers. That is why I have written the symbol R for real numbers. Next slide, please. Next slide, please. If you work as a computer scientist, you might have seen these kinds of processes. Quicksort is a program that is used for sorting of lists. Next slide, please. This is also an example of a process. You have raw material, you have eggs and bread, you can do some cooking and create breakfast. Next slide, please. So when you connect these boxes, taking care of the inputs and the outputs, you get diagrams. And these diagrams are also processes. What matters is that only connectivity is important. So you can pull these wires, you can move these, you can shuffle these wires, but you have to be careful about the connectivity. And you have to be careful that the input wires stay as inputs and the output wires stay outputs. Next slide, please. Like I said before, types should match. Otherwise, the diagrams are not defined. So for example, if you try to connect the process cooking with quicksort, we don't get anything meaningful. Next slide, please. So a process theory is simply a family of processes which make sense together. You connect these boxes and you get a theory. Some nice examples from mathematics are functions and linear maps. If you are a physicist, you probably know about optical devices and how you can play with light by having optical devices in succession. That is also a process theory. Proofs, as in mathematics, also make process theories. Next slide, please. So formally, a process theory is a set of system types. System types, as I said, are the wires, and a set of processes. Processes are the boxes, and these processes are closed under forming diagrams. Next slide, please. So closure means that if you connect these boxes, states, you get, this is what I have shown graphically here. Next slide, please. Next slide. Let's look at some interesting processes. A state is a process that has no input. This can be seen as creating a quantum state according to our requirements. Another important process is an effect. An effect has no outputs. This can be understood as doing a test. So this pi effect is essentially a test for checking whether our state is a pi state. Next slide, please. Then there is the trivial example of numbers. Numbers can also be considered processes with no inputs and no outputs. And when you connect a state with an effect, you get a number. You can consider this number a probability. Next slide, please. And so this is essentially the generalized Born rule. The Born rule is basically used for calculating probabilities of certain outcomes in quantum physics. The multiplication of two numbers can be represented like in the last bullet, as I've shown. And the number 1 can be represented to be in empty space. Next slide, please. So the question is, what can process theories or just diagrams do for us? Let us see. So the first important feature of these diagrams is that they help us realize the difference between separable and non-separable states. A separable state is one which can be represented by this equation. So the state psi, so this is a two-party state, or this is a two-party state, and if you can express it like this, this is a separable state. A non-separable state is basically an entangled state. We will see in the next slides how process theories differ for separable and non-separable states. To work with non-separable states, here we introduce something called a cup state. A cup state psi is one for which there exists a cap state. So a cup state looks like a cup, and a cap state looks like a cap. And when you connect the two, you get a line. We can use this notation for cup states and cap states, and the equation that I showed on the previous slide becomes like this. Now this is very intuitive if you look at it carefully. Could you go to yes? So this so the last equation is very intuitive. Essentially, what we are doing is we are yanking the wire. We are just pulling the wire with a jerk, and essentially all of the equations we will look in the next slides will be simplified using yanking the wire rule. Now here's the theorem. If a process theory has cup states for every type, which means for every kind of information or every kind of data or every kind of wire, and every state separates, then a process theory has trivial dynamics. Next slide, please. Yes, so I won't be going into much detail here, but what I want to show you is the power of this graphical reasoning. Now, this is essentially a mathematical proof of this theorem. And I mean, look at this. It doesn't even look like mathematics. So this kind of simplification. So this theorem is based on the graphical notation that I've shown to you in the previous slides. So this theorem shows that if we have separable states, then the process theory we have is very trivial. In classical theory, in classical mechanics, or in classical systems, all of our states are separable states. Now, this theorem shows that if we have a separable system, we cannot have quantum phenomena, or we cannot have interesting phenomena that we see in quantum physics. So we have to work with non-separable or entangled states. Next slide, please. And an important kind of state, an important process in quantum theories is getting a transpose of a process. So now here I want you to think in terms of matrices, because transposes are easy to understand in terms of matrices. Now all the processes, all the boxes that I have shown you can be expressed in terms of matrices. And from matrix theory, we know that a transpose, in trivial terms, a transpose is essentially changing the inputs and outputs, interchanging the inputs and outputs of a process. Uh, in graphical terms, this can be shown like the first definition. And in the second equation, what I have shown is the transpose of a transpose. Now, if you yank the wire, the golden rule of quantum picturalism, if you yank the wire, you can see that the transpose of a transpose is the original process. So in the yellow box, we have taken transpose of F, and outside the yellow box, we have taken another transpose. So this equation shows us that, so this is essentially a proof, actually, that the transpose of a transpose is the original process. Next slide, please. Next slide, please. So transpose essentially is a rotation. If we rotate a process, we can be confused because a box is essentially a square in our case. So we try working with this smart notation where we have this kind of a parallelogram instead of a square, and we define it to be, so when we take the transpose, we know that we have taken the transpose. We don't have to show the wires as in a bent form. This is also very intuitive, as I've shown in the last two equations. So you can slide the boxes along the wires very intuitively. Next slide, please. Now I'm not going to define adjoints, but another important mathematical feature of quantum theory is adjoints of states and processes. So an adjoint essentially converts a state into a test for that state. So for example, if I have a state psi, and if I want to check that if I want to test for the state psi, what I need is adjoint of that state. Next slide, please. So we have these kinds of similar processes with inputs and with single input and single output, and these can be shown to be so I call these sister processes because they have similar elements, and we can move between these processes by taking conjugates or adjoints or transposes. Next slide, please. So here I have shown how these sister processes are related. I'm not saying that you can interchange these processes in a diagram, but this is a useful diagram to remember how these processes are related, or how to have a conjugate of a process if you have the original process. Next slide, please. Now we have a problem. Suppose that the numbers we get by connecting state complex numbers. Now, in the generalized Born rule that I have shown you before, we said that these numbers are probabilities, but from probability theory, we know that the numbers have to be real numbers. Next slide, please. So to solve this problem, what we do is we multiply this diagram with its conjugate, essentially a complex conjugate. Next slide, please. And this gives us the conventional bond rules, which is mathematically shown here. So when you multiply a complex number with its conjugate, you get a real number. So the problem of having real probabilities has been solved. Next slide, please. Okay, so now we have another problem. We have built our process theory based on this expression. Now we are talking about doubling. So now to counter this dilemma, what we do is we create another process theory with doubling included. Next slide, please. So a doubling. So for a double process theory, what we do is we just create duplicates of all the processes, which are actually the conjugates of. So we take the conjugate of the whole process and put it next to it. For expressing these graphically, I have used a broader tip. So these are definitions of doubled states and effects. Next slide, please. Okay, so now I have expressed Born rule again in this doubled formalism. Next slide, please. Okay, so doubling is basically, as I said before, a doubling of wires, doubling of boxes, doubling of processes. Next slide, please. Next slide. So the good thing about doubling is that it preserves diagrams. So while we created our process theory using those thinner wires or single wires, we can get the double process theory just by, writing drawing the diagram with a thicker pen. And we know that all these thicker wires and thicker boxes mean doubled wires and doubled boxes, respectively. Next slide, please. But doubling kills global phases. So like I said before, doubling is essentially multiplying with complex conjugates. So if we have global phases, they disappear because of complex conjugation, as I've shown in the last equation. Next slide, please. Another interesting feature of doubling is that we get a process called discarding, which can be represented like with this symbol. So discarding means that we don't care about the information or the state anymore. So we discard the system. And discarding means that we just connect the two wires. And so essentially, whatever information was traveling in that wire, we have lost it. Next slide, please. We can check that for normalized state, discarding means that we lose the input, we lose the state. Can we have the next slide, please? Now, finally, let's try looking at quantum maps. So whatever we have talked about so far has been very general. You can use this formalism for other theories like theory of linguistics, theory of cognition, but now we are going to look at some quantum effects. So a process theory of quantum maps essentially consists of doubled wires, which represent Hilbert spaces, and doubled processes. So the normal processes that I've shown you before, and the discarding process. Next slide, please. An important feature of any physical theory is that it is causal. So causality means that there is, the intuitive relation between cause and effect. Every effect is due to some cause. An important consequence of causality is that there is no signaling. Next slide, please. So let's suppose there are three parties: Alice, Bob, and Hamza. Hamza Hamza creates an entangled state represented here by rho, and sends half of it to Alice and half of it to Bob. So this is a two-party state, and Alice and Bob do measurements on their respective subsystems. Now, no signaling says that any measurement that Alice performs on her subsystem cannot be used to send a signal to Bob or send any useful information to Bob. Now, this can be proven using, like I said, causality shows. Causality implies no signaling. Next slide, please. To see this, we apply discarding at Alice's site. So we know from laboratory quantum physics that whenever you do a measurement, you destroy the state. And now let us apply our definition of causality to this system. Next slide, please. So applying the definition of causality, we see that it is almost as if Alice never did her measurement, which means that the state that the subsystem that Bob has, it's essentially the same. So Bob gets no information. Next slide, please. So in other words, it can be stated like this, that Hamza has a two-party entangled state. Hamza sends one part of the state to Bob, and Hamza destroys the other part of the state. Next slide, please. Now let's look at interaction. Like I said before, the process theory for quantum systems is a double process theory. So a thicker line for the information, whereas for a classical system, we can use a thinner line, a system with no doubling. And these two wires or these two systems are not equivalent. Next slide, please. These are important definitions for interaction. So like I said in the very first slide, that you have to look at the system from bottom to top. So the first definition shows that we have a system, we have a classical state, and we encode it to a quantum state. In other words, we have classical information and we encode our classical information into a quantum system. The second definition shows that we have a quantum state and we do a measurement. We know that after the measurement, we get classical information. That is why we have a thinner line on top of the second definition. Next slide, please. Okay, so here's an exciting problem, or rather an application of quantum physics. Okay, so in quantum teleportation, what we try to do is we have two parties, Alice and Bob, and Alice wants to send a state to Bob. Now we know from laboratory quantum physics that whenever Alice does a measurement on her state, she destroys the state. And here we want to have this state represented by rho. We want to transfer it to Bob without destroying it. We want to transfer the state intact to Bob. The protocol of quantum teleportation is basically that Alice and Bob share an entangled state. So in this diagram, you can see that there's a cup-shaped wire between Alice and Bob. This cup-shaped wire is essentially the entangled state that we have talked about before. And now we have to think of a protocol or a methodology to transfer this rho to Bob. Naively, we can, well, let's try forgetting everything we have talked about so far. Let's try showing this diagram to a kid, as a puzzle, uh, as a puzzle. You ask a kid, we want to move this row state to Bob. What do we do? What do we put in these question marks? Now, a kid would connect the wire coming out of row with the other wire in Alice's section, and also connect basically remove the question mark from Bob's side and just connect the wire. And that is essentially what quantum teleportation is. Can we have the next slide, please? Okay, so I have essentially drawn what I've said before. So here, the U hat represents a unitary operation. And okay, can we have the next slide, please? Okay, so in quantum teleportation, the protocol goes like this. Alice performs a bell-type measurement on her side, which is represented by the small yellow box. And Alice gets a classical output for a measurement that she does. That classical output is represented by the thin line coming out of the circle on Alice's side. Okay, and so when Alice gets an outcome for her measurement, she knows what that outcome is, and she can tell it to Bob, which is what is represented by that thin wire going to Bob. And Alice also knows U hat because she can decide the kind of measurement that she wants to do on the state row. What she does is she tells about the measurement and the outcome to Bob, and what Bob does is Bob creates an adjoint of that unitary process. Bob encodes that classical information that Alice gives, and then Bob essentially gets the state. Now, I mean, I have explained it in words, but let's look at it graphically. Can we go to the next slide, please? Okay, so like I said before, we can play with these equations by yanking the wire. So I have yanked the wire hard, and so this is essentially equal to the previous diagram. Can we go to the previous diagram? Yes. So what I have done is I have taken the row state in one hand and the wire that is going out to Bob in the other hand, and I have pulled it hard with a jerk. Next slide. So this is the same expression that we had in the previous diagram. Next slide, please. Now, by definition, the adjoint of a unitary operator is its inverse. So, when we compose a process with its inverse, we get an identity, and essentially we have simplified that expression. So this diagram shows that we have teleported the state to Bob. So that row was previously on Alice's side. Now it has moved to Bob's. Can we go to the next slide, please? Another important, so we know this from experiments, complementarity in quantum physics. So if we have two complementary observables, so let's say we have encoded a system in one basis, which is complementary with another basis, and if we try to measure the state in a different basis, we get no information. This is what is shown in this diagram. So on the left side, the empty circle represents one basis and the filled circle represents another basis. So going from bottom to the top, we have some classical information. We have encoded it in some bases. That is why we get a thicker wire. And now we try to measure it in a different basis. So the right side shows that there is no transfer of information. Can we go to the next slide? I have also expressed this in words. Encode in empty circle, then measure in filled circle. There is no data flow. This is the principle of complementarity. Next slide, please. Now, the principle of complementarity is best seen in the famous Stern-Gerlach experiment. So many different versions of Stern-Gerlach experiment can be created. Let's try thinking in terms of spin. So let's say we have a source shooting electrons. We know that electrons have spins. So the Z box represents a process that you can consider it as a kind of a polarizer, which transmits two beams. One is polarized in, let's say, the positive Z direction, and the other is polarized in the negative Z direction. So the two beams represent the two different polarizations. Now let's say we block one of the beams, and we know that it is either the beam pointing upward or downward. So let's say we block the downward beam, and we let the other beam go into another box. Now this box is in the X basis. We know from quantum physics that the Z and X are complementary bases. So and it also means that the upward polarization is a superposition of the positive X and the negative X polarizations. So after the box, again, we have two beams. We block one of the beams, and then we let the beam go into another Z box, and then So the surprising feature of this experiment is that if you look at the first box, we have blocked one of the two beams coming out of the Z box. And if you look at the last box, so we know that it's the same beam coming from the source. But again, we have two beams coming out of Z. Now we let the two beams hit a screen. Let's try representing this in terms of pictures in our formalism. Can we go to next slide, please? Okay, so so the left side of the equation show that we have some quantum information. We do a test for the Z state. So putting a block means that we know that the other beam is. So we have essentially polarized the beam to be in the positive Z direction, which is what the measurement means. And then we let the quantum information go into the X measurement. I have represented the X box as the yellow filled box, and then we let it go into. So the right side of the equation is obtained by applying the principle of complementarity. So looking at the right side of the equation, we see that there is essentially no transfer of information from the bottom to the top. Next slide, please. Quantum key distribution is another important application of quantum physics. So quantum key distribution is essentially a secure method of transferring information from one party to another. Once again, we have Alice and Bob. So in quantum key distribution, Alice and Bob have a certain key which lets them decide a basis for their encoding and decoding. So looking at the Alice's part, Alice has some classical information. She encodes it in a basis represented by the empty circle. Now we have a thicker wire which represents quantum information. And I mean, if there is no eavesdropper, so Eve represents eavesdropper. So if there is no eavesdropper, the information goes to Bob, and Bob can do the measurement. Now, if there is Eve, and there would be some times when Eve doesn't know the basis that Alice and Bob use that because that key is only known to them. So if Eve tries to do a measurement of the information that is being sent and she does it in a different basis, there is no flow of information or useful information from Alice to. Next slide, please. Now, what we have done is we have just applied the principle of complementarity. Uh, the diagram on the right shows that there's no flow of information from Alice to Bob, and more importantly, Eve is not able to get any information as well. Next slide, please. So if we add a group structure, so if we use group theory with complementarity, we get something called ZX calculus. Can we get the next slide, please? I'm not going to talk in much detail about ZX calculus, but I'll just show you some examples. So ZX calculus is based on these simple equations. So these are all the principles needed for ZX calculus. And why do we need ZX calculus? We need ZX calculus because it is very efficient for simplifying quantum circuits and working with quantum algorithms. Next slide, please. So here's an example of ZX calculus. This is a representation of a quantum circuit in ZX calculus. Next slide, please. So as I said so many times that we have to look at the diagrams from bottom to top. So at the bottom, we prepare a state. On top of that, we have some quantum gates. Quantum gates are used for quantum computation. And on top, we have a measurement. Now, in quantum computing, we want to simplify our circuits. And so here, I have just applied the principles that I showed you, like the right-hand side. So, it's quite easy to work to simplify quantum circuits like this. Next slide, please. Now you may ask, all of these things that I've shown you can be done with other techniques as well, but yes, they are difficult, but that is also doable. So what else can quantum picturalism do for us? Next slide, please. You can also do measurement-based quantum computation, as I said before, quantum algorithms. You can also do tests of non-locality. I'll show you an example in the next slide. You can also do automated theorem proving. There are softwares for that. Next. Okay, so I think the most bizarre feature of quantum theory is obviously entanglement, and entanglement leads to non-locality. Einstein was famously known to have said that it is spooky action at a distance. So non-locality means that states of entangled systems. So if we have a multi-party system and if we do a measurement on some part of that system, that affects the outcomes of other parts of the system. So yes, so it's just like saying that if you have two particles, which could be light years away, and if you do some measurements with one of the two particles, it affects the outcomes of the measurement that you are going to get with the other particle. Now, this is really bizarre. In 1964, John Bell showed that quantum physics, as we know it, violates principles of locality. So he came up with certain inequalities called Bell inequalities. and you can create different experiments to test for those Bell inequalities, and quantum physics has been shown to violate those inequalities, which means that nature really is non-local. So GHZ non-locality uh, is one of those tests. Uh, it is named after Greenberger, Horn, Zeilinger, and so what it tells us that if we have a quantum theory, we get a certain outcome. If quantum theory is correct, we get a certain outcome. On the other hand, if we have a local theory, if nature is local, then we would get another outcome. So you can experimentally test it. Now, so obviously you can predict the outcomes of certain experiments using traditional mathematics, but you can also do it with quantum picturalism. So here I have shown you the predictions based on quantum theory using pictures. So this large diagram is basically the algorithm, the procedure for doing the experiment. So on the bottom we have these states represented by yellow circles. On top of that, we have certain processes or certain rotations, and on top of that we have measurements. The empty circles are basically measurements, and the topmost yellow circle is basically measurement in a different basis. The lowest circle with a pi shows the outcome that we are gonna get with quantum theory. Next slide, please. Okay, so this is prediction based on a low. As you can see in the lower circle, the one with 0, this is totally different from the prediction of quantum theory, which was a pi outcome. So so this is essentially the GHZ non-locality theorem. This is basically the whole theorem writing that you would do with mathematics if you were not doing with these pictures. Next slide. I'm going to stop here. Once again, I would like to signpost you to this wonderful book if you want to learn about these things and think about it more deeply. You should try getting this book. None of the content that was presented here is mine. I am merely a messenger. Now I would like to have your questions. Thank you.
Okay. Okay. So somebody's asking if these slides are going to be shared. Then yes, they will be. Okay, so Mia Umar Khatab says that my question is, if a charge is placed in a train moving at a very high speed, does this charge create a magnetic field for a person inside the train and for one outside the train?
Okay, so for the person inside the train, it won't create a magnetic field, but for the person outside the train, it will.
Okay. So there are a few questions which I have from my side. So first of all, that the entire quantum picturalism, what are the prerequisites that are required for anyone to understand this? Like, I understand that it is supposed to be very basic, but can it be taught to freshmen, or do they require to have certain knowledge about quantum physics or quantum theory?
Well, I think if you have studied high school physics, you can, you can study this textbook cover to cover, so you can basically understand all of this. You don't even have to have a physics background to study this.
Oh, that's amazing.
Yes, it can be taught in freshman year. It is being taught in second year, I guess, at the University of Oxford to computer scientists who have no physics background.
Oh,
and
wow.
the and the pioneer of this formalism also says that this could be even taught to kindergarten kids. So they are actually working with some kids and trying to show that this can be taught to kids.
Okay, so that is actually very interesting. So I hope that this can also be introduced in Pakistan so that more and more people understand what is so fascinating about quantum theory and quantum physics, and eventually also quantum computing. So Dr. Muhammad Javed asked that why third party Hamza is important for sharing data between Alice and Bob in quantum teleportation. So what's your role between Alice and Bob?
Okay, so yeah, so the problem is that obviously, I mean, Alice and Bob could have the states shared between themselves. I mean, there is no need for a third party. So the third party diagram that I showed you was something else. It is not essential in quantum teleportation. But yes, an entangled state has to be present between Alice and Bob. Otherwise, if Alice does a measurement on her state, it destroys her state. So you have to have an entangled state to do this kind of transmission of information.
Okay, so we have another question that do you think we can build some 2-qubit systems building upon your book?
Sorry, I couldn't hear your question.
Okay, so they're asking that how self-sufficient is that book? Like, do you think we can build some 2-qubit systems building upon your book? Building on this book and stuff.
Yes. So if you work with ZX calculus, you can create all kinds of quantum computing circuits. Basically work with any number of qubits in principle. And the book is quite self-contained. I'm not sure, but I think it also has appendices that review linear algebra. So, I mean, obviously you can play with these pictures, but to have a deeper understanding, you need to understand some mathematics. And the book also has some advanced content, which is marked with some stars. So you can skip that content if you are a beginner. But yes, so the rigorous theory for studying this kind of quantum physics is category theory, which is actually quite an advanced theory. It is usually taught to fourth-year mathematics students.
All right. Okay, so I believe that they were also asking about your single photon lab book.
Okay.
Could that be used to build 2-qubit systems?
Yes. So in my book, we have worked with 2-qubit systems. So we have done 3 tests of non-locality. We have done 2-qubit tomography. So I think it's the chapter 5 and 6 in my book which deal with these things. So yes, you can do it.
Okay, so for those of you, if you missed the introductory part, then yes, Hamza Waseem is also an author of the book called
I have this.
Single Photon.
I can
Yeah,
show
you have that? Oh, yeah, please do.
Okay, so here's some shameless marketing.
Yeah, so it's a well-deserved marketing, quantum mechanics in the single photon laboratory. It has been published by the Institute of Physics, and
Yes.
yeah, so it's not shameless marketing. You deserve this one. Okay, so Waqar Ahmed asks that how we can understand what is the exact meaning of spin 1 or spin 2 particles.
That depends on what kind of that depends on what kind of formalism and what kind of basis you are working with. So I mean, traditionally, to study these kind of things, you work with a standard model, you work with particle physics, but there are alternate formulations. So yes, I think you need to study particle physics for that.
Okay, so I think that the viewers would like to know a little more about your book. So if you could tell them more about it, that what exactly was the motivation behind it, and what did you hope to achieve through it? And also, there's a question by a viewer who says that they can't seem to find it apart from Amazon, so how can they buy it?
Okay, so the book is basically a spin-off of my undergraduate final year project. So while I was studying at UET, I wanted to do a project in physics, and I was quite fortunate to work with Dr. Muhammad Anwar at Phys Lab in LUMS. So he already had done some groundwork for single photon experiments, and he actually suggested this project to me and my a couple of my batchmates who worked with me. So this was essentially we started out, working for our thesis, but then it became, it became too comprehensive for our thesis when we. So after submitting the thesis for my university, we kept working on the project, and yeah, and in 2 years we had a 200-page manual. So the late who was the president of Phi Society suggested to us that maybe you should pitch it to uh, a reputable publisher, because this is something out of the box, and this is something very much relevant for countries like Pakistan where we don't have these kinds of labs. Yeah, so that was the motivation uh, to help other labs in the developing countries create their single photon experiments. Mosna, are you there? I think we have lost Mosna.
Uh, I'm really sorry, there was some technical issue on my side. So, okay, so there are some more questions. So, Dr. Mohammed, he asked that if third party is not important, then how will no cloning theorem restrict data sharing?
Okay, so I am not sure. I think you are confusing two things. So the no cloning theorem is important when you are talking about quantum key distribution. So in yes, it is important in teleportation as well. I mean, essentially, if Alice could create a clone of her state and then measure her state, and create so many clones of her state and then do measurements, then she could get a complete characterization of her state, and then she could send it to Bob. But she can't do that. So no cloning theorem is there, and obviously it's a no-go theorem, and it stays there. But I think I don't understand your question. Mosna, are you there? Mosna, are you there?
Yeah, I'm really sorry. We're having some issues. Yeah. So I believe this is the last question. Uh, Admiral Hyperspace, that's the username. They asked that, okay, so first of all, they're asking that how can they get the book because they want to build a laboratory similar to that built by you in PIAS. And they're asking that how do you think a theorist could do this in his undergraduate that would get him to win scholarships like you did?
I think you can get the book from Amazon, and you can also look at the IOP website. They also have an IOP bookstore there, so you can get the book from there. But I think you can also request the library at your institute, because these books can be bought as ebooks in collections. So there are quite a few other interesting titles as well on quantum physics in the same series. And yes, you can do it with undergraduates. These experiments are meant for undergraduates, and but I think the aim for doing these experiments or creating this laboratory should not be to get a scholarship. uh, I mean, it's wonderful that you want to do these experiments with your students, but the motivation should be to understand quantum physics. And I think if they are really passionate about it and they work hard, they can get any scholarship.
Okay, so once again, thank you, Hamza, so much for this very informative session. And I would like to thank everyone who joined, and we would like to apologize for the little technical glitches which occurred during this webinar. So again, thank you, Hamza, and thank you, everyone. We really hope that
Thank
it
you
was
so
a
much for
useful
having.
session.
Yeah, thank you so
The
much for
pleasure is
having me.
all ours.
I hope everyone enjoyed.
Okay, thank you. Okay. Allah Hafiz, everyone, and thank you once again.
Allah Hafiz. Bye.
Allah Hafiz.